Welcome to Chemistry Lecture 2-3A, Accuracy and Precision. Chapter 2, 3 represents the number of the lecture. A means there's probably going to be part B. Our learning objective is to define the difference between accuracy and precision. What is the difference between that? Our goal here is also to practice percentage error. How do we calculate how wrong we were in an experiment? And finally, we're going to discuss errors in measurement in general. We're leading up into learning how to write numbers in a scientific fashion and how to make good calculations. All right. So, there are no exercises today. So, without further questions, let's move on. Okay, our objectives are to distinguish between accuracy and precision. Our objectives are to determine the numbers of significant figures in measurements, to perform mathematical operations involving, to perform mathematical operations and using significant figures to convert measurements into scientific notation and to distinguish between inversely and directly proportional relationships. Rock on, let's move on. Okay. Accuracy and precision. Accuracy refers to the closeness of measurements to the correct or accepted value of what we're measuring. What that means is, if I get on a scale and it tells me 246 pounds, am I really 246 pounds as according to the National Weights and Standards Committee when they would know? The better my scale, the closer it will come to reality. That's accuracy. Precision refers to the closeness of a set of measurements of the same quantity made in the same way. What that means is, if I make the same measurement over and over and over again, do I get the same result? If I measure myself 10 times and I get 246.5 pounds every one of those times, that's a pretty precise device. It will continually give you the same result every time. So accuracy refers to, so let's look at a picture of what that might mean. Check it out. Here's something from our book, A Difference Between Accuracy and Precision. In step 1, the darts are thrown at the dartboard. When they hit the bullseye, that means they hit the bullseye, so that is accurate. That's where they needed to go. And if they hit the bullseye many times, that is precise. They hit the same place 4 times in a row. Right place, many times. That's accurate and precise. So let's go back. Okay, check this out. This is a very precise throw. It threw in the same place over and over again, but its accuracy was pretty off. It didn't hit the target. It wasn't where it needed to be. And this was both not precise, because the throw went in many different places each time, and not accurate, because it didn't really hit the target. Any questions so far about accuracy and precision? Nigel? No? Okay. Let's continue on. All right. We're going to skip that one. Accuracy and precision. Okay. So in science, it's really important that we reflect how accurate and how precise our measurements are. And part of that is using percentage error. That is calculated by subtracting the accepted value from the experimental value and dividing the difference by the accepted value and then multiplying by 100. Okay, don't write that down. That's confusing. Go ahead and write this down, this little equation. That'll make more sense. What that means is, how right were you really? How correct were you in actuality? For example, let's say that your task is to weigh this marble. And previously, an expert came in and told me this marble was 10 grams. Perfect, accurate, measured by the National Weights and Standards Committee. Okay, if you measured it and you came up with 9.5 grams, you've got an error. And you need to know what percentage your error was. So you take the experimental value, that is what you got. You subtract what was accepted, that's what the world says it was. And then you divide by your accepted and multiply times 100. Let's see if we can see a problem of that in action. Here's a sample problem. Take a moment and see if you can figure it out on your note paper. How about I write down the formula for percentage error? What was it? Value experimental minus value what?
I know that's as far as I got.
Value accepted divided by value accepted times 100 times 100, and that's going to equal our percent error. Okay? What do you think? All right, good students. One person came up with 7.14. Let's see what the pros came up with. 7.7. So, well, did you do the math like this?
Yep.
And what did your computer come out? What did your calculator come up with?
Well, the first one is 0.10 divided by 1.3
Mm-hmm.
times.
It sounds like 0.1 divided by 1.3, doesn't it? Okay. Well, did anyone else get 1.4? Is this a mistake in the book? So Timmy says he got 7.69, and that's a lot closer because they rounded up to 7.7. All right.
Yeah.
Yep, there we go, there we go. All right, so whenever it's asking you to calculate percent error, it's going to ask you to do the value experimental minus the value accepted and divide by value accepted. Any questions about what percent error is or how to get it? No? All right, let's roll on. Okay, accuracy and precision. Some error or uncertainty always exists in a measurement. It depends on the skill of the measurer, conditions of the measurement, and measuring instruments. Yesterday in lab, we did something pretty interesting. We did 5 different measurements of the same stuff. Let me go get our measurement board and find out, well, how we did. Just a moment. I know, I'm now walking into the lab. Oh, we are. Thank you very much.
Just pointing out.
In this area, underneath the measuring devices.
Marble there. Do you have it?
There's marbles in the drawers. Yep. Yep. All right. Those of you in YouTube land, I bet you wonder what I was doing. So, check it out. Here are our measurements from lab. They all look a little bit different. Someone got 11.94 for the length of the room and 8.35 for the length of the room. That looks like Timmy and his group, but Nathan and his group got 11 meters and 72 centimeters for the width of the room. I'm not sure if the room was really 72 centimeters. There must have been a mistake. Check it out. Here we go. Kara's group got 92 milliliters, and Nigel's got 97. There's 92, 98, 99, 99, 99. Nigel and Nathan. All right. And check this out. Over here in the temperature column, we've got 1, 0, 2, 5, 1, and 5, and 0.5.
It's 0. It's 0.5.
I got negative 1, but I forgot I heard 0.5. I think
Stirred the ice.
the ice.
Oh, no, it's negative.
may have
It was negative.
The ice may have changed temperature over time. Well, in fact, if there was ice in the beaker, if there was ice in there, it was at 0 at all times.
Yeah.
But if there was no ice, then it would have raised the temperature. I tried to keep ice in it the whole time. Dry ice would be colder. So, check it out. Even us, when we had simple things to measure, we had error. We had the skill of the measure or conditions of the measurement. For example, those of you who are measuring the width of the room with a meter stick, that's not a good way to measure the width of the room. Much better to measure the measuring tape. But your measurement conditions weren't that great. Or your measuring instruments, not that great. Measuring the marble with the graduated cylinder and splashed all over. Yeah, your conditions weren't the best. And
like
so,
maybe if we had like something surrounding you to catch the water.
yeah, that's a great idea. Or a bigger cylinder.
The problem with water coming out though is then your original measurement wouldn't have even counted.
That's right. So,